Alright, today we'll discuss section 8.8, which is about improper integrals. So what is it different from the other integrals we saw? Well, in other integrals, we had a nice function, a continuous function, on a closed bounded interval a, b, and then we discussed Riemann sum approximation, so on and so forth, how to evaluate, right? But now, for improper integrals, it might happen that one of the limits or both of the limits of integration could be plus minus infinite. Another instance is your function may not be sort of continuous, or it may be at some point your function might be blowing up. So then can we say that the integral doesn't exist, or we still can do something? So that's what we're going to discuss in this section. Learning objectives are infinite limits of integration, and in particular we'll discuss how do we know if the integral of 1 over xp exists for which values of p. And then we'll discuss integrand with vertical asymptotes, so the cases when the function blows up. And then we discuss tests for convergence and divergence of improper integrals. So let's get started. Essentially, we have two cases for improper integrals. So one of them could be like the case of ln x over x squared. So the question here could be, what is the area under this curve when from 1 to infinite, right? So to find out, you would be integrating from 1 to infinite ln x over x squared. You see, the ln x over x squared, as x increases, it sort of tends to 0, right? Gets very close to x-axis, but it never touches. So it's never closed, right? It just goes on, goes on. So then you might say, okay, I mean, you keep adding some areas here, so maybe it's infinite. So if it's infinite, I would say this integral sort of doesn't exist, or I could say infinite. But if it, maybe it's finite, so we need to find it out, right? So we need to have slightly different way of making sense of such things. What does it mean to integrate from 1 to infinite, right? Another occasion is, let's say that I want to compute the area of this function 1 over square root of x between 0 and 1. Again, so around 0, if you let x go to 0 from right, this blows up, right? So again, this graph, when you go to the left, right, close to 0, it blows up, but it never touches y-axis. So again, there is something, some part is going infinite, right? So the question then remains the same. So can I make sense of this integral, square root of x dx? So what does that mean? Can I define it at all, right? Because again, as I said, at x equal to 0, 1 over square root of x is not defined, right? It's not defined. So again, we want to discuss such integrals, and in which occasions we can say that yes, it has a value, and in which cases it doesn't have a value. So for the first picture in the previous slide, here is the definition. That's called the improper integral of type 1. So when at least one of the limits of the integration is infinite, like here it's the infinite from a to infinite, or from minus infinite to b, or it might be that both of them are infinite, right? Minus infinite to infinite. So how do we make sense of it? Well, this integral, by this integral we mean this limit of integral. So you evaluate the integral from a to some point b, where b is a variable, and then once you integrate, you take the limit b goes to infinite. And for the minus infinite to b, you do exactly the same, but for the lower limit, right? So you integrate from a to b, so your b is fixed. You vary a, let a go to minus infinite. And if this limit exists, we say that, okay, this limit, this function, the integral exists. We say it converges, yeah? Now for the integral over minus infinite to infinite, what you can do is you can pick any c. It doesn't matter. You can pick any c. So you break your integral, evaluate from minus infinite to c, and plus c to infinite. How do I evaluate each one? According to these two rules. Okay. So if in all these cases, I happen to find some limits, right? If I manage to find the limits, if they exist, I say that improper integrals converge. Otherwise, if these limits doesn't exist, at least one of them, let's say, fail to exist, then I call that this improper integral is divergent or diverges. Okay, let's do some examples. All right, is the area under the curve ln x over x squared from 1 to infinite finite? If so, what is its value? Right, so the question is asking us to compute the integral from 1 to infinite of ln x over x squared dx. By definition, it simply means the limit as b approaches to infinite of the integral from 1 to b ln x over x squared dx. So now what we do is we first evaluate this integral thinking as b some constant, and then we let b go to infinite if we manage to calculate. How do we do it? Well, this is integration by parts. Let's let u is equal to ln x, dv equal to the rest 1 over x squared dx. Then du is 1 over x dx. Here v is minus 1 over x. So then this integral right here, so let's rewrite, so from 1 b ln x over x squared dx. Well, this is uv, so minus ln x over x minus v du, right? V du, so minus minus is going to be plus 1 over x squared dx. And the limits of integration, here it's evaluated from 1 to b, here it's 1 to b. From the first one, I get minus ln b divided by b, and if you let x equal to 1, it's simply 0, right? So it's plus 0. From the second integral, what is the integral of 1 over x squared is minus 1 over x. I evaluate from 1 to b, so what I get is minus ln b over b. At b, it's going to be minus 1 over v. At 1, it's going to be minus plus 1. So then, again, so rewriting this equation right here, integral from 1 to infinite of ln x over x squared dx. This is simply now the limit as b goes to infinite of this quantity minus ln b over b minus 1 over b plus 1. If you let b go to infinite, where does ln b over b goes? Well, by L'Hopital, if you apply L'Hopital, the derivative of ln b is 1 over b, the derivative of b is 1, so this is like 1 over b, and the limit of 1 over b is 0 because b goes to infinite. So this goes to 0, that goes to 0, so I'm left with 1. So in particular, what I say is, yes, area is in fact exists, right? So area is equal to 1. So in particular, the integral converges, right? So this integral converges. Let's evaluate 1 over 1 plus x squared from minus infinite to infinite. So in other words, I'm trying to find this blue area or shaded region, right? As you can see again, this 1 over 1 plus x squared is never 0, so it's never going to intersect the x-axis, but it will approach very close to x-axis, right? Okay, so what do we do? Well, by definition, I can break it as from minus infinity to some point c, but let's simply pick 0. Dx 1 plus x squared plus 0 to infinite dx 1 plus x squared. You could do symmetry here. I mean, you could say, okay, this is symmetric, so if you calculate one of them, you can multiply by 2. But anyway, so let's do. So what do we get? For the first one, we need to write it as, let's say that a goes to minus infinite, integral from a to 0 dx 1 plus x squared plus limit here b goes to infinite, 0 to b dx 1 plus x squared. Right. So what is integral to 1 over 1 plus x squared? Well, this is arc tangent of x from a to 0, and here it's also arc tangent of x evaluated from 0 to b. So arctangent 0 is 0, hence for the first one we get arc tangent of a with minus here. For the second one, again arctangent 0 is 0, so this is going to be arc tangent of b. Okay, so the first one limit asking for which theta, or for which theta the tangent of theta is sort of minus infinite, approach to minus infinite. Remember for the arc tangent. So you realize that this is the case when a is approaching minus pi half, but I have minus here, so it's going to be pi half. And the second one is what is sort of an arctangent of infinite? In other words, for which theta angle the tangent approach to infinite. Well, this is when theta approach to pi half from left. So summing up, I get pi. So the area under this curve is pi. All right, now the integrals of the form 1 over x to the p. We want to find out when the improper integral converges and when it diverges for which values of p. Well, first of all, let's say that p is not equal to 1. Because when p is 1, you get 1 over x. This is ln x. It's different, right? The integration is different. I cannot use power rule. But then, let's evaluate the integral from 1 to b, right? And then I would let b go to infinite. So this is 1 over x to the p dx by power rule. So this x to the minus p, right? So this x to the minus p plus 1 divided by minus p plus 1. And since p is not 1, this minus p plus 1 is well defined, right? I mean, it's not 0, so I'm not dividing by 0. From 1 to b. So this gives us b to the minus p plus 1 divided by minus p plus 1 minus, if you let x equal to 1, this is simply 1 over minus p plus 1. Now, now you let b go to infinite. So what happens? Well, if p is bigger than 1, then this minus p plus 1 would be less than 0, right? So this exponent of the b is less. So I could write this as 1 over b to the p minus 1. Then exponent is positive. Then this 1 over b to the p minus 1, that would go to 0, right? This would go to 0. So if this is the case, then this limit 1 to the b, 1 over x to the p dx, in fact approaching, so the first term becomes 0, the second term, so you'll get a minus 1 over minus p plus 1. So there is minus, so it's going to be plus at the end. Now, again, let's take b infinite, but now in this occasion, let's say that p is less than 1. P is less than 1. In this occasion, minus p plus 1 is positive, right? So I have this b to the minus p plus 1. This is positive. B is large number, it goes to infinite. So then b to the positive power goes to infinite too, right? So this goes to infinite. So then the first term blows up. So then you get, so then this limit xp dx, it becomes infinite. So it diverges, right? So, okay. Now, yeah, so basically what we can say is, so if p is bigger than 1, converges, or you can say the improper integral exists. If p is less than 1, it diverges. And when it converges, in fact, we know the limit, right? This is the limit right here. Now let's do what happens if p is equal to 1. In this case, this integral becomes ln of x, right? From 1 to b. Well, at 1 it's 0, so this is simply ln of b. But if you let b go to infinite, ln b, this goes to infinite also. So again, it diverges. Okay? So the conclusion is, if p is bigger than 1, the improper integral converges to minus 1 over minus p plus 1. Otherwise, it's going to diverge. So it doesn't exist. All right, now integrand with vertical asymptotes. So the cases when the function is blowing up, but it's still finite interval, right? So I restrict myself to 0 to 1. I want to integrate this particular function, 1 over square root of x. But what we notice is, if you let x go to 0 from right, it's going to blow up to infinite, right? It's going to blow up to infinite. So there looks like something wrong with this. Although it looks like this is a nice looking integral, the limits are nice. But the function is blowing up because of this vertical asymptote. So what we do it means I need to be a little careful with vertical asymptote. So I do as I did in the previous case. I fix some a which is bigger than 0, and then I try to find this area right here, and then I keep moving a towards 0. Eventually I'll get in the limit the whole area. If it's infinite, I say the integral diverges, right? The same idea. So let's see. So I can think of this again, limit as a goes to 0 from above, integral from a to 1 over square root of x dx. Well, what is this integral right here? So let's see, calculate it. Well, antiderivative of this is what? X to the 1/2 times 2, I guess, right? So now evaluate from a to 1. This is 2 minus 2 square root of a. Now if I let a move to 0 from right, what happens? This integral, this number goes to 2 minus 2 times square root of 0, so this moves to 2. So it means this integral, this area is finite, and it's in fact equal to 2. Alright, so then here's the general definition. So this is called, when we have infinite at certain point, right? If we have some vertical asymptotes, it's called integrals, improper integral of type 2. But except on a, I'm assuming that the function is continuous. So I have this continuous at a. Then basically you integrate c to b, right? So you pick c larger, and then you approach a from right. If it's the other way around, if your b is problematic, at b you have function discontinuous, like both of etc., then you integrate from a to c, and then you approach to b from left, right? What if this bad point, right, this discontinuity point, is not the one of the endpoints of the interval, but somewhere inside. Well, then you split your integral from a to c and c to b, and then you apply the previous two rules for each. Okay, rules. And again, as before, if once I carried out these integrals or limits, if the limits exist and happen to be finite, I call this integral convergent, and then otherwise I call this improper integral divergent. Okay, let's do some examples. All right, I would like to investigate the convergence of integral 1 over 1 minus x from 0 to 1. What is wrong with it? Well, if x is equal to 1, then the integral becomes 1 over 0, right? So I have to be careful with 1. So I do it the way we do in improper integrals. So we say p goes to 1 from left, integral from 0 to b, 1 over 1 minus x dx. Let's keep the limit for now. What is the integral of 1 over 1 minus x? You can do u substitution where u is equal to 1 minus x and so forth, but it's not hard to notice that this is minus ln 1 minus x from 0 to b. At b, you get minus ln 1 minus p. At 0, this is simply ln 1, so this is minus 1 plus 0. Now, if you approach to 1 from left, right? So b is approaching from left. Then 1 minus b approaching to 0. But if it approaches 0, then ln, because ln 0 is infinite, right? So then, yeah, this is in fact minus infinite, right? So this is 1 minus b, so that would be minus infinite. I mean, regardless plus minus infinite, but it just blows up. So it means this limit does not exist. So we say that this integral diverges. Okay, now I want to consider integral of 1 over x minus 1 to the 2/3 from 0 to 3. And the problem is with x equal to 1, right? X equal to 1 is on this interval 0 to 3, and at x equal to 1, the function blows up. So as you can see on the picture, that's vertical asymptote. So what we do is, we write it as two separate integrals, right? I can write it as a integral from 0 to 1 plus integral from 1 to 3. And for each one, I need to write as a limit. So let's write limit b goes to 1 from left, from 0 to b of dx over x minus 1 to the power 2/3 plus limit in second occasion, so they use c. Let's use c approach to 1 from right, integral from c to 3 dx x minus 1 to the power 2/3. So once you do it, all you have to do is now just evaluate each integral and then take the limits. In fact, if at least one of the limits fails to exist, I immediately call them that the improper integral diverges. You don't have to evaluate the other one. But if both exists, you manage to find the value, then it means the improper integral converges to that sum of the values. Okay? All right. So let's evaluate the first one. So we know that the interderivative of 1 over x minus 1 to the 2/3 is x minus 1 to the 1/3, and I think I need to multiply by 3. Evaluate from 0 to b, so this is 3 cube root of b minus 1, At 0, this is -1, so plus 3. Now, if I let b go to 1 from left, the first one becomes 0, vanishes. I left with 3, right? Now let's take the second one. In the second one, I get the same antiderivative, 3x minus 1 to the 1/3, evaluated from 3 to c to 3, which gives me 3 cube root of 2 minus 3 cube root of c minus 1. Now, if I let c go to 1 from above, then the second term vanishes, so I am left with 3 cube root of 2. So I see that both terms exist, right? I managed to show that both limits exist. Hence, we saw that the integral converges, and it converges to 3 plus 3 cube root of 2. Right. Tests for convergence and divergence. So this is similar to comparison tests that we discussed for the limits, convergence of the limits. Okay, let's say that my f and g are continuous and such that both of them are in fact non-negative functions, and the f is sort of smaller than g, right? So if you were to sketch, so f would be something like this, g would be something above, right? It's larger. So then, if the integral of g of x converges from a to infinite, then the same is true for the integral of f of x, right? This sort of makes sense. If sort of the area under g is sort of finite, then the area of smaller function f is also finite. And in the opposite direction, if the f is divergent, so it means if the area of this f is sort of infinite, then clearly the area of gx, right, because gx is bigger, will be infinite, right, diverges. Let's do some examples. I would like to integrate sine square x over x square. Well, integrating of this particular function is difficult, in fact. So let's say that I want to only investigate whether the improper integral converges or diverges. Okay, that's all I'm interested. I don't want to find its value, because finding value might be difficult, but showing whether it converges divergence might be easier because we know the comparison, right? We can apply. So indeed, what we can do? Well, this is non-negative, right? So we know that this is non-negative. This is sine square x over x square, and we know that sine x is less than or equal to 1, so sine square is less than or equal to 1, so this is 1 over x less than 1 over x square, right? So now, if you integrate 1 over x square, well, this is minus 1 over x from 1 to infinite, right? Okay, so we would do like b here. We would do like b here, so it would be like 1 minus 1 over b plus 1, so it would go to 1 as b goes to infinite, right? So it converges, right? So this converges, hence we can say that this integral converges. Okay, let's look at the second one. Well, 1 over x squared minus 0.1 is bigger than 1 over x squared. That's equal to 0, right? And the same applies if you take the square root, right? So this is 1 over x, as far as x is bigger than 1, right? However, so this is 1 over x. Now if you integrate 1 over x, we know that this is infinite, right? Because this is here p is equal to 1, right? Like if you like the p-test, here we could also apply the p-test here, like p is equal to 2 here, right? So at p equal to 1, this is infinite, because this is the integer becomes like ln of x, and ln of infinity is infinite. So this diverges means that diverges, right? Hence this particular integral diverges. Okay. How about the last one? Well, on 0 to pi half, the cosine is positive, right? So this is, so cosine of x over square root of x is positive function, and this is less than 1 over square root of x. So if I manage to show that integral of 1 over square root of x is convergent, then the original function would be convergent. So let's try it. Integral from 0 to pi half 1 over square root of x dx. The antiderivative is square root of x times 2 from, so I have a problem at 0, right? So I need to do something like a to pi over 2, and then I need to stick here a limit, right? So I need to stick here a limit. So limit as a goes to 0 from right. Okay, so then what do we get? At pi half, I get 2 square root of pi half minus 2 square root of a. If a goes to 0, 2 square root of a goes to 0, so this goes to 2 square root of pi over 2, so it converges, right? Hence, this is the converges, so by comparison, the original integral converges. So we don't know where it converges, but we know that it's at least less than or equal to this quantity that we found. Here is, in my opinion, a better approach, which is called a limit comparison. So what is it? Let's say that you have two positive functions. Again, they must be positive. And then you divide f by g. Let's assume that the limit exists. Okay, so it's equal to L. Then the convergence or divergence of two improper integrals are sort of equivalent. So if one converges, the other converges. If one diverges, then the other diverges. Okay, so let's do some example. Okay, I want to show that the integral from 1 to infinite of 1 over 1 plus x squared converges by simply comparing it with 1 over x squared. I mean, you don't have to do this way because we know that this antiderivative is arctangent, and then you can simply do the way we did before. But this is just to show the power of limit comparison. Okay, so what I do is, let f of x to be 1 over 1 plus x squared, my g of x to be 1 over x squared. So what I do is I divide f to g. I take the limit because my limit here is infinite, so I let x go to infinite. Okay, so then what happens? F of x is 1 over 1 plus x squared is 1 over x, so this becomes like x squared divided by 1 plus x squared, right? Well, for example, I could apply the L'Hopital. You don't have to, but you can apply L'Hopital. It becomes 2x. Here it becomes 2x, so x cancel, you get 1, right? So this is my L. Anyway, so the limit exists, right? It's finite. So it means if one converges, the other converges. However, if you notice, this particular one is much easier in some sense to integrate. So simply minus 1 over x, 1 to infinite if you like. So it's like a minus 1. Or you can simply say it by this, because p is equal to 2 bigger than 1, by this p test for improper integral, it converges, right? So it converges. So converges. That implies the original integral that we are looking for converges. Okay, the last example is we'd like to investigate the convergence of 1 minus e to the minus x over x from 1 to infinite. Well, e to the minus x is going to 0 as x goes to infinite, so it means like this 1 minus e to the minus x over x is behaving like 1 over x when x is sufficiently large. So it means I can compare it with 1 over x. So let me pick my f of x to be 1 minus e to the minus x divided by x. Let me pick my g of x to be 1 over x. And then again, I take the limit of f over g. So I get x's cancel. I left with 1 minus e to the minus x, which is 1, right? Which is 1. So it exists. So it means by limit comparison, if one integral converges, the other converges. If one diverges, the other diverges. But by p-test, right? By p-test, because p equal to 1, this integral blows up, right? It's infinite. So the original integral will also blow up. So it diverges. In other words, we call it divergent, right? Diverges. That's it.